Okay. Yeah, so for today's AI seminar, we're joined by Vishal Gupta. He's an associate professor of data science and operations at USC Marshall and Dean's Associate Professor of Business Administration. He received his PhD in operations research from MIT. Professor Gupta researches data-driven decision-making and optimization, particularly in data-scarce settings like precision healthcare and real-time decision-making. He'll talk about his work on a framework to work with ill-behaved, hard-to-optimize losses and decision-focused learning. So for any attendees, you can leave your questions at any time in the chat or in the Q&A, and I'll try and bring them up in real time. And then if you want to, you can like voice them too. We'll try and unmute you. And that's also will be like Q&A at the end. But yeah, real-time questions are welcome. So with that, I'll let Professor Gupta take over. And yeah, thank you.
All right, thank you very much, Eric. So it's a pleasure. I was just saying, Eric, I haven't been to ISI in person in quite a while. So it's a pleasure to share some research with you guys. Towards the end of the talk, I'll mention a little bit more about sort of open directions we might pursue in this space that I think are a great collaboration. So as Eric mentioned, I'm going to be talking about something called perturbation gradient losses, which is a unifying perspective for decision-focused learning. This is joint work with my former PhD student, Michael Wong, who's now at CUNY Baruch. And to give some context of the talk, I'm going to first start talking broadly about decision-focused learning, and then we'll kind of zoom in into this idea of perturbation gradient losses. So to set the stage, I'm an ops person, right? So I want to like motivate this by thinking about a couple of examples. So the first one I want you to think about broadly is vehicle routing. So in vehicle routing, you typically have a depot, you're going to send trucks out, the trucks are going to visit a set of customers along this graph, and then come back home to the depot. And there are lots of canonical formulations of vehicle routing. They basically look like minimized travel time subject to a series of constraints, like the capacity of the trucks, the windows in which you can visit certain customers, the sequence of orders of customers, things like that. So it tends to be a very hard combinatorial problem. And if you're the kind of firm that solves vehicle routing regularly as a part of your logistics, you probably have an in-house custom solver to solve that combinatorial problem, or you're licensing one as like third-party software. But like this problem really is a sort of optimization problem under uncertainty, right? So the fundamental uncertainty in some ways is the travel time. When I send a truck out along a route to see these set of customers, I don't actually know how long it's going to take for them to do this. So this is unknown at decision time. But it's not truly just kind of arbitrary in some sense. I do observe partially informative information. Right, so I'm going to call these things context. You'll know things like the current weather, like recent traffic information, maybe information about closures or alerts along the route. Okay, so the operational setting then, if we kind of take one step back and think about that firm, is they're solving this decision-making problem under uncertainty repeatedly. Right? So they solve it each day when they send out their trucks. And it's a similar but not identical problem. Right? So things that are similar, like the road network is largely similar, the number of trucks is largely similar, but the things that are probably different are things like these contexts that are determining travel times and like patients and customers, things like that. All right, so now hold on to that application in the back of your mind. And let's think about the second application. We can think about ESG index tracking. So for once upon a time, I worked in quant finance before I was an academic. So what's the index tracking problem? Index tracking is a problem where, as an investor, you would like to invest in an index like the S&P 500, which has 500 assets in it. But you say to yourself, look, I don't really feel comfortable investing in alcohol, tobacco, firearms, firms that have a history of child labor practices. Right, so I would like to get an exposure that looks a lot like the S&P 500, but I don't want to invest in all of the 500 assets that compose that. And so the question is, how do I construct a portfolio whose performance tracks the S&P 500, but does not have these kind of bad or like undesirable assets in it, or perhaps has a lower number of assets in it? And again, they're like somewhat standard formulations of this problem. They tend to be convex as opposed to the hard combinatorial problem we saw before. And again, this is a problem of optimization under uncertainty. Here, the fundamental uncertainty is the returns, both of my portfolio assets and the target index that are unknown at decision time. And again, we have partially informative context, right? And here, in kind of contrast to the previous example, the contexts tend to be very high dimensional. They're often proprietary and like heavily custom engineered, right? So depending on the firm that you're talking to, they might use broad things like market indicators, right? Things like what is the Fed fund rate at the moment, but they might also use things like tweets or voice analysis of CEO shareholder calls. So there's a very rich set of contextual information that might be coming here. And again, the operational setting is that you're going to solve a similar problem each day, right? You have to rebalance the portfolio at regular intervals, either daily or weekly or monthly. And then you're thinking about that problem is largely the same structure. The difference is the historical data. These contexts are changing, and these asset returns are changing. Okay, and then like one last application I'll give you to think about, because I think it's fun, is to think about EV fleet charging, right? So in EV fleet charging, you have a fleet. I guess in this picture, I have a fleet of trucks that are all electric powered. I want to plug them into the grid to charge up these batteries. There's some combinatorial constraint on this, right? Because I need each of those vehicles not to like overload whatever my local charging capacity is or what my local number of plugs are. But I also need them to be available at the right times, fully charged, so I can send them out on the routes that they need to do. And there's like a benefit to being strategic about this, right? So I show here a time series of electricity prices. And if you look at electricity prices throughout the day, there is a lot of randomness in that time series, but there's also opportunities where it spikes and falls. So if I'm very careful about when I charge these trucks, I might be able to minimize my charging costs. Okay. And again, so this is optimization under uncertainty. I don't know these electricity prices as I start planning out this day. I observe partially informative context about the weather, day of week, special events. These drive a lot of things in electricity prices. And operationally, I'm solving a very similar problem day to day, but there are sort of differences. Okay, so if I take a step back now from these three applications are examples of something we call contextual stochastic optimization. So in contextual stochastic optimization, you observe a context, and we call it X, this random variable. It's observed at decision time. Once you observe this context, you choose a decision that I'm going to call pi of X, and this pi of X has to satisfy some feasible constraints, right? So think about the vehicle routing problem. Pi of X has to satisfy all the combinatorial constraints for it to be a true path around this arc. Sorry, true cycle around this. Okay. After I choose this decision, I send out things, and then I'm going to incur costs. These costs are going to depend on what I decided to do, this pi of X, and also this unrealized uncertainty random variable Y, right, that I didn't get to see ahead of time, that I was hoping X was informed. Okay, and then I repeat the whole game again, right? I'm going to see a new context, I make a new decision, I incur new costs in this. Okay, so there's a couple of things I want to make clear real early in the talk, because they tend to trip people up as they're thinking about this problem if you haven't thought about it before. One is that in the examples I've given you, X and Y are exogenous, right? We're going to sort of understand that we are small enough logistics firms that where we send our trucks does not fundamentally affect traffic in LA, right? So because these two random variables are exogenous, there's no benefit to exploration. This is not really a bandit problem, right? I do have to learn something about how Y and X are related, but choosing pi of X is not going to help me do that, right? So I'm free to choose pi of X in an entirely exploitative way. The second thing I want to point out is that the decision-making problem is known, right? So we have really good formulations of vehicle routing problems, of that ESG tracking problem, of even that EV fleet charging problem. They sometimes involve complex constraints, unlike regression and classification, but I do have an optimization problem that I feel comfortable saying models this application, right? So this is not really model-free RL, okay? I do know a lot about the way the system operates. So there are many problems that look like this when you start thinking about it. Fulfillment kind of looks like this. Problems in optimal energy flow for energy systems look like this. Various portfolio optimization problems look like this. And these problems can be best thought of maybe as a hybrid between regression. I'm trying to learn something about how the unobserved Y relates to this observed X, right? And stochastic optimization. I kind of want to make good decisions subject to uncertainty and a bunch of constraints. Okay, so let's go back in time 10 years, right? It's a fairly new field. 10 years ago, if you were confronted with one of these problems, how do you solve it, right? So the traditional way these sorts of problems are solved is sometimes called the estimate and optimize pipeline. And I'll say like every consulting project I've ever done, where they're solving a decision-making problem of uncertainty, they're implementing some version of this. Okay, so what does this pipeline look? You have a bunch of offline training data. Okay, so these are going to be pairs of these X, Y. And then you go and you fit your favorite machine learning model that predicts Y from X. Okay, so there's a whatever you want to choose here, you choose. And then what do you do at decision time? Okay, you do this once, this offline training. At decision time, you observe a new context. You say, okay, I don't know what Y is going to be, but I use my machine learning model to predict Y as best I can with this f of xn plus 1. And then I call a solver, right? So this might be the solver that I had that was the custom in-house solver for vehicle routing. It might be an off-the-shelf solver if I can model my problem in that way, but I call a solver with this prediction. Now, the strengths of this traditional pipeline, right? This was what I learned when I was a PhD student, right? Is that one, it reflects common practice. Like I said, every firm I've ever been to kind of does something that looks like this. Okay. Second is that you have complete flexibility about what you want to do for this ML. So the offline training stage, if you want to fit linear regression, great. If you want to fit a really fancy neural network, great. If you need to fit some interpretable model due to particular application or organizational constraints, that's fine. Do what you want to do. And then the second thing is you get to reuse your custom solver. So if you were that vehicle routing firm and you had already invested hundreds of thousands of engineering hours, right, into thinking about how to build a really great solver for your particular variant of vehicle routing, you can just use that as a plugin into this pipeline. Okay, so like very great, two really broad strengths. The drawback of this pipeline, which is in some sense the backdrop to the rest of the talk, is that as you start to think about it, you realize that this offline training stage is entirely blind to the the real-time decision making. Okay, so what do I mean by that? When you fit the ML model, you didn't care if the outputs of that ML model were going to be used for vehicle routing or if the outputs of that ML model were going to be used for electrifying the grid, or the outputs of that ML model are going to be used for like laying down street lamps or planning out paving of roads or whatever it is, right? So there's no notion in which the structure of that downstream optimization problem affected the way you did your offline training. And so that raises the question, like, is that really the best we can do, right? Or if I know that I'm going to ultimately use this ML model for an optimization problem, can I do something smart? And that's brought about this field that's kind of grown up in the last 5 years, right? Maybe 5 to 10 years, which is decision-focused learning for contextual stochastic optimization. All right. So the question here is, can I exploit the downstream optimization structure, knowing that I want to actually solve vehicle routing, or knowing that I actually want to solve ESG tracking, to learn better, right? To develop better learners? And the short answer is yes, right? There's very strong empirical evidence. If I was giving an empirical talk, I could show you great examples at scale for the power system, for supply chains, where you can do this and you do much better than following that naive pipeline. Okay? And something that's kind of come out of that empirical evidence is we realize the most benefit seems to occur when data are scarce, when there's low signal to noise ratios, when these covariates X are high dimensional, or when this learner that you're trying to learn in that first stage is inherently misspecified. So you have some interpretability constraints. You have to use a simple learner. And in those settings, doing something where you take advantage of the downstream structure leads to much better performance overall in these systems. Okay? So once we have that, then the question is like, how do you design methods to do this? Right? There's many ways I could think about trying to extract structure there. And there's been a ton of proposals in heuristics dating back a long time. So like I used to put a survey in this talk, right, as a set of literature, and I realized that like, okay, every time I did it, someone in the audience would be like, wait a minute, I solved this problem back in 1971 or something, right? So like there's been a ton of literature here. It tends to go under different names in different fields. So some people call it operational statistics, people call it the predict and optimize pipeline, people call it amortized optimization or task-aware learning. I think decision-focused learning is the latest version of this. There was a while where it was called decision-aware learning, etc. Okay, many proposals here. They differ dramatically in the computational requirements and the kinds of problems that they're going to solve. And then I'd say Broadly speaking, there are essentially no performance guarantees for these methods in the settings that I described above. Okay, so when you're thinking about settings where data are scarce or covariates are high dimensional or the learner is misspecified, the methods that we have, we don't really know theoretically why they perform well in those settings. And so this just raises a fundamental knowledge gap. Like, how should we think of this?
I think
So what
there's
method?
a question in the chat
Yeah, great.
from Jay. I don't know if he wants to ask it live or are
Jay.
we allowing people, or maybe, oh yeah, I'll allow him to talk.
Yeah, I I think I just got permission to speak. Yeah, so before you were making this point about how the inputs and the outputs are exogenous, but now you're saying something about how this isn't, I guess, maybe you answer the question that this isn't really changing that assumption about that exogenous nature, but now you're using this term structure, um, and I guess I'm a little confused about maybe what you exactly mean by structure. And maybe you're about to get to that.
Uh, let's see if I can do it in a picture first, and then we'll get to like proper math later. So by structures, by the exogenous thing here, I mean that if we just think about the left side of this board that I have here, x and y are random variables. There is some conditional distribution out there of y given x. And I'm saying that like I observe x and y, right? If you like, there's a joint distribution of x and y. And when I observe data, I just observe it as draws from that joint distribution. So nothing I do is affecting that joint distribution. It's not going to be shifting over time. I'm just thinking about it as a joint distribution. When I say we could exploit structure, what I mean really is if I think about the right side of this board, right, the optimization I care about is defined essentially by the cost function C that I have there and this calligraphic Z, which is the feasible region. Okay, and what I'm pointing out is that in the training process of traditional methods, we never talk about that cost function or that feasible region. And so the question is, can I look at that cost function and that feasible region in some sense and tailor my training method to do better than if I just assume that these x and y are coming from the distribution? And I'll
Okay,
like
so the
define
assumption
what better
is,
means explicitly with math in like 4 slides.
and so you're assuming the model is fixed. So this isn't a model selection problem. It's just a way of improving the optimization given the model.
The model here being little f.
I mean, I guess I'm thinking of the model as, yeah, sure. The model is little f.
No, we're going to be learning little f. So the
Okay.
question is how to learn little f so that this pipeline works really well. Maybe give me 2 more slides and I will,
Okay.
I promise Jay, I'll come back to you once I write that math. All right. Okay, so what are we going to do today? I'm going to try to formalize what we've talked about so far in a mathematical model. That's sort of not novel. I think that that's been done a lot in the literature, but I'm going to specify it clearly for you. But what I am going to talk about is a new approach to solving those sorts of problems, which is really about how do I learn that little f. Okay, and that's going to be via minimizing this surrogate loss called this perturbation gradient loss. And unlike the kind of existing methods in the literature, these PG losses exhibit a performance guarantee. So I'm going to be able to prove a performance guarantee under misspecification. And that performance guarantee hinges on a simple property, the data distribution that we'll talk about. The nice thing about these losses is that they dovetail like seamlessly with modern SGD pipelines. So when you want to learn a neural network for little f, you can just plug this loss into your SGD pipeline and things will go great. And you get really good numerical performance. And if that was the whole talk, I would call this like a B plus talk. I don't know, an A minus talk. It's like interesting, but it's sort of just one more drop in the bucket. We had a zoo of methods to solve these problems. Here is another animal in the zoo. Okay. But I think the real niceness of this talk and why I wanted to present it is that when you start thinking about these PG losses, they provide a unifying perspective of a lot of methods in the literature. So you can go back to the literature and you can realize that a lot of those surrogates can be viewed as adaptations of this PG loss. And that gives them like some theoretical understanding of why those methods perform well in certain circumstances and why they perform badly in others. And it suggests an algorithmic sort of tweak you can make to those different methods to improve their performance, specific tweaks for specific. And then more broadly, like once you start thinking about this, you realize there's lots of natural generalization. So you can use PG losses to prove performance guarantees for various non-surrogate methods for these problems. There's like lots of extensions to nonlinear settings, double weight robust estimators. So like overall, my perspective is that PG losses are the right mental model for thinking about surrogates for decision-focused learning and contextual stochastic optimization. Okay, so that's where we're going to go in the talk. And this is like the thing. So first thing I'm going to do is establish this model so I can enter J with math as opposed to with pictures. And then I'm going to talk to you about these PG losses. And then we'll do a little bit about this unifying perspective. And I'll do some preliminary benchmarking. Okay, so here's the model, and then we'll go from here. So first thing is I'm going to be thinking about minimizing this cost function. So x, again, is my context. I observe this at decision time. Pi of x is the decision I make. That pi of x is constrained to be feasible in some set script z. And then I pay costs. And the costs I'm going to assume are bilinear in this way. It's the inner product of y and pi. Okay, so it turns out this bilinear case is mathematically interesting, but also kind of covers most of the applications that I talked about so far. Right, so if you think about vehicle routing, like traveling along the arcs, you can write along this way. And the only assumption I'm going to make about this problem otherwise is that z is known at decision time, and it's possibly combinatorial. So like you should really think about z as the set of constraints that like this forms a proper vehicle routing path. So think about it ugly and nasty. And then the other assumption I'm going to make about this problem is that we have a solver. So I'm going to treat it as a black box, but there is some in-house solver that, given a prediction for what's going on with y, solves the deterministic version of this problem. Okay, so I tell you this is what's going to be the arc cost at all the arcs, you tell me how to route the vehicles. Okay, we're going to work in a data-driven setting. So these x, y are going to be IID draws from some joint distribution. This is that exogenous assumption. Okay, and my goal is to learn a good policy pi. I have to define good for you. And then this question is like, what's the right policy class for pi? Okay, so I think this is the next thing to think about. So in this formulation, as I've written it, pi is just a mapping from context to feasible decision. So like the natural 2026 ML intuition is like, well, throw a giant neural network at it. Okay, one that takes in context, does some magic, and then outputs a feasible solution. And this is an approach. There are people in the literature that think about this, but it comes with a bunch of challenges. So one challenge here is that ensuring feasibility is a constrained prediction problem, right? So I want the outputs of this neural network, if, for example, if this is like, which arcs do I travel in my road network for the vehicle routing, to be feasible. It should actually form a path. It should actually visit the customers in the designated time windows. The capacity of the trucks have to be non-violated. This is like enforcing these sort of constraints on the outputs of a neural network is traditionally a hard problem, right? We can do it via various relaxation techniques and things, but in these operational settings that I care about, even mild infeasibility is often unacceptable, right? So you really have to think about this feasibility, and it creates a host of issues. Okay. So what are we going to do instead? I'm going to say, like, this is not impossible. There are people in the work that think about doing sorts of neural networks. What we're going to do instead is we're going to think about a class of plugin policies. Okay, so this is that same problem we were talking about. Okay, what is a plugin policy? I'm going to fix a hypothesis class of learners, script f. And my goal for any given f in that hypothesis class, I'm going to define a policy, pi f of x, which is going to be computed as z star of f of x, where z star of f of x is the solution to this problem. Okay, so the way that you should interpret this is that you should think about this as, You should think about this as, I see my x, f of x is my best guess for what's going on with y, and then I call my solver. And whatever I get against that solver, that's what I get. Okay? So think of f of x as an estimate of the conditional mean of y. And you can ask why this set of policies. A lot of people have thought about them. The first natural reason is that they generalize that traditional pipeline, right? So if you're thinking about an organization that was previously fitting a learner and then calling a solver, we're doing the same thing here, right? There is a learner and then I call a solver. So in terms of change management, it's like a fairly natural thing to manage, to get an organization to adopt this sort of change. The second mathematical reason, if you care about this, is that the full information policy to this problem, if I said, okay, let me just think about any policy that looks like this, actually is of this form where f of x is the true conditional mean. That's like a short proof to show that. So that limiting to this set script f is like really the only thing that we're doing here. We're taking policies of the same form, but we're going to limit our learner to this set script f. And the best thing I think practically for me about this is that it naturally handles these complex feasible regions, right? So insofar as my learner, right, it just has to kind of produce an estimate of y, which is an unconstrained regression problem. And then this function z star, right, which calls my solver, will handle feasibility natively. Okay, so I don't need to think about how do I handle feasibility in this problem. It's just going to come for free in my policy. And now here's where we talk about like what is good. Okay, so this is going to make my answer to Jay a little bit clearer. So my goal is to learn this function f, and I want to learn a function f that has low regret. Meaning what? If I were to deploy this pipeline, right? So I learned an f and then I deployed this policy. In real time, what happens? I see an x, I deploy this policy, I incur these costs. So these are the expected costs I'll get at deployment. And what is this? If I think about the best possible choice of f within that policy class, this would be the cost of that. So I'm thinking about the regret relative to best-in-class Oracle with infinite data, infinite. And my goal is to kind of learn an f that is small with respect to this metric, right? That has small regret. Right, so these are mostly like a, let's say, disclaimer, so nobody yells at me later. There's still some misspecification error, right? I picked this script f, so I'm going to talk about how does the choice of script f affect the learning problem. This nice thing about this is that we're separating the learning problem from the modeling problem. Like I'm not really going to talk too much about the script f, but the other nice thing here is that it integrates the traditional pipeline, right? I'm thinking about this f, learning a good model, right, in a way that gets me very close in terms of my actual operational costs. Okay, so this is a good place to pause. So first, Jay, have I answered your question?
I think so. I mean, I guess maybe the question I was asking is this sort of similar to model selection? And my takeaway is that it sort of is, right? Because you're providing a family of models and trying to, choose between them in your optimization. So do you think that's a fair assessment?
So I think we could cast it that way if we said script f is a family of models, and I'm trying to find the f in that family that minimizes this regret. And the reason I'm like, not just like, yeah, thumbs up, that's the right way to think about it, is we often think about model selection where script f is like an enumerable set, whereas I'm going to think about script f as like all the neural networks with some fixed architecture. Right, so I'm going to have a nice way to search over this family in some sense, right?
Right. I mean, I guess some people will search over, neural networks by number of parameters and maybe, structural aspects about like layer sizes and layer connectivity. So,
yeah. So I just want to say, like,
that
as
could
long as
be
we agree,
unbounded, but you could bound what the limits are there too, right?
exactly. So as long as we agree script f is big, then I agree with you. Yeah. Think about this as model selection, right? Where the selection criteria is this regret.
Okay. I'm good with it.
Any other questions? I want to make sure this model, which is kind of fundamental in the literature and for us to talk, is clear to everybody.
If anyone has a question, they can type it or raise their hand. We can unmute them. I don't see any at this point.
Okay, so if no one's going to ask a question, I will ask a question, and I will ask the rude question. Okay, so why is this hard, right? In some sense, like you're just changing the loss. Like if I think about standard ML, like the ML I teach my first year grad students, right? Like they would solve a regression problem by minimizing MSE. You would formulate it in some way like this way, minimize FSE. You'd approximate this expectation by ERM over some training set, and then you'd like run SGD, right? You like pick a class where this is differentiable, you'd run SGD over the parameters to find a nice f. Okay, and if you think about the problem I just stated to you after a lot of fanfare, right? What was it? It looks exactly like this, except I've changed this mean squared error loss to this loss that's implicitly defined in terms of the solver of this optimization problem. But like implicitly, you could just kind of follow the same strategy. Form an ERM over the training set, like run SGD, like get something out, call it a day. And so in one word, like why is this hard? Well, it turns out this map around solvers is traditionally badly behaved, particularly for combinatorial optimization problems and linear programs. Right? So it turns out the gradient-based methods fail catastrophically. I'm going to show you this, I think, in an example rather than mathematically. You don't need to parse the example very much, other than to say the optimization problem is sort of the dumbest optimization problem I could think of. I have two options, option 1 and option 2, and I want to choose the cheaper one, but I don't know exactly their costs, y1 and y2. I see some context that tells me about y1 and y2. And then I'm going to solve this over a set of hypotheses that's deliberately misspecified, right? Kind of speaking to that earlier thing that I said, that empirically we see misspecification is the key idea driving some of the benefits of decision focus. All right, so if you actually care, this was the simulation setup. I encourage you not to read it, right? And just look at the right side of the slide. So the policy class that I picked was over one parameter, so I could make a pretty picture, okay? And this is the in-sample training loss. Okay, now it may not be obvious at this resolution, but this loss is piecewise constant and discontinuous. That means like even in these places where it looks like it's doing something, if you zoom in, this is actually a piecewise constant. So now if it's piecewise constant and discontinuous, it means that the gradient is 0 almost everywhere. Okay, so every point is a local optimum. If you run SGD on this loss, or if you just tried to solve the ERM problem, it stalls immediately because every point is a local optimum. So there's no gradient information to be had. And you can ask, why does this happen? Was this like a function of my silly optimization problem? And it's not, it's sort of intrinsic, right? So if you think about what's going on with linear programming or combinatorial optimization problems, if you change your estimate of y just a little bit, you're basically changing the cost coefficient a little bit. But if you change the cost coefficient a little bit, it tends to be that you pick the same discrete solution or the same vertex of this LP that you would have chosen before. It's only when you change it a lot, and then when you change it a lot, you leave kind of a cone described by this polytope, and you swap from having this configuration of a solution to a completely different vertex. And that's what causes the jumps here. So you have like constant flat regions, or I should say like constant flat regions, followed by a jump. Okay, and then if you change more, you have a more constant flat region, followed by a jump. So this behavior is intrinsic, right? So what do, right, if you want to do this? You can't do the naive form an ERM, run SGD. How do you optimize such a loss? Like I said, this has been a topic of conversation for quite some time. And the natural idea is form a surrogate, like find a loss that looks kind of like this one, but has better properties of optimization. And the first sort of proposals for surrogates in this literature were convex. So here are some references. You can think about MSE as a surrogate. You can think about this SPO plus paper, this Fenchel-Young Loss is a lot of things here. And the problem with these things is that in the misspecified setting, the setting we care about, they tend not to work well. Okay, so you can see in all these cases, they're giving you the wrong minima in some sense of this function. And that's maybe not their fault, right? When you delve a little deeper into the theory for this problem, it turns out that optimizing the empirical problem is NP hard. So if it was possible to find a good convex loss, this would somehow challenge the hardness, because optimizing a convex loss should somehow be easy, right? So probably no convex loss is going to be able to represent this thing well uniformly over instances. So that led people to start thinking about non-convex losses, right? And again, there's been like a whole zoo of methods that do this. They tried to do this. They have various success, but as you can see, like in this particular example, none of them actually get the right minimum either. Okay. So what's the challenges here? So many of these methods perform badly under misspecification. Essentially, they have very limited performance guarantees. This SPO plus method, for example, works, but only under well specification. This CELO method works, but requires you to solve a monolithic optimization problem that's like an IP, the size of your training data set. So maybe that doesn't make sense. And I think the biggest thing for me as a perspective as a researcher is like, well, the motivations for all these methods are all over the place. So SPO plus is motivated via like a very careful duality argument. CELO is motivated by a very subtle bi-level optimization argument. This Fenchel-Young loss comes from an argument around Gibbs distributions. This DVB loss is an interpolation argument. It's just all over the place. And so since they're all over the place, it's not really clear how to think about them or compare them in some ways. So this brings us to the perturbation gradient losses, right? The thing I'm going to propose in this paper. So obviously they do very well. They look like the target loss in some way, but are smooth and well behaved. They in this particular example identify the correct minimum, and we sort of show that they generically identify the correct minimum. And then I think the thing I'm going to talk about later in the talk is that it turns out all of these other methods can somehow be related to this method and seen through this lens. And that gives you a nice way to think about them. All right, so that's the model. That's where we're going. It's a good time to take questions before I kind of formally define how did I make the nice pictures for our proposal. All right, so let me show you where these come from. So I'm going to need a little bit more notation. This will be like the most mathematically dense thing. Okay, so the loss that we're interested in, that horrible ill-behaved thing, is this inner product between y and then the solver called at t. Okay, so if I think about the solver called at t, I could also think about this is the optimal solution from the solver. I could think about what is its optimal value at t. So that would be t transpose e star of t. Okay, and if I think about this optimal value, you just have to follow me why I want to do this for a moment. I could think about its directional gradient in the direction y. So I'm going to think about v applied at t plus lambda y, where this lambda I'm going to take to be infinitesimally small. Okay, so what is that directional gradient? Okay, so here's some fake math. Be very clear, this is fake math. If I think about g prime of 0 and I was differentiating this beast, I would have to take like the first thing times the derivative of the second thing, so I get here, plus the second, I guess the derivative of the first thing, which is respect to lambdas here, times the second thing, and then evaluate this lambda equals 0. And then here's where we're kind of going to leverage the fact that we know something about this optimization problem. So based on that picture I told you earlier, we believe that if I have small perturbations in the objective function, shouldn't cause the solver to change. So this contribution sort of should be 0. And if this contribution is 0, I'm just left with this term. And this term evaluated at lambda equals 0 is exactly my loss. Okay. So this was fake math. It's fake math because this term is not differentiable. So it doesn't make sense what I wrote here. But you can turn this math into be formal math using Danskin's theorem. So that this is a correct statement. And then the conclusion is that the loss that you actually care about, there's an identity. I can reframe it equivalently as the directional derivative of the value function. And why is that useful? This is hard to think about. But instead of thinking about this loss with these jumps and things, let me think about not approximating this, but let me think about approximating that directional derivative. Okay, and that directional derivative is a derivative with respect to a one-dimensional parameter lambda. So you can kind of go back to calculus 101 and be like, when you made those secant lines on graph paper to approximate derivatives, be like, how do you approximate a derivative? Well, the two versions I'm going to talk about in this talk, you can do some backward differencing for the secant line with a step h, or you can do some central differencing for the secant line with a step h. And these two things are going to be our surrogate losses. These are these perturbation gradient losses. Now, this is actually a family of losses. There are many ways to form zeroth-order gradients that are approximations in one dimension. These are the ones that we're going to talk about today. In fact, I'm really just going to talk about. Okay, and it turns out these approximations are well behaved, right? So assuming your optimization problem is bounded, it turns out their approximations are Lipschitz. They're differentiable almost everywhere. They have an explicit gradient. They can be represented as the difference of concave functions, which is helpful algorithmically. You can prove that this backward loss upper bounds a true loss. You have a nice robustness or pessimistic learning guarantee. And you can ask, why do you get all this nice behavior when the original thing was so badly behaved? And the intuition is that, well, solutions to linear programs and combinatorial optimization problems do have this jumping behavior, but these losses were defined as a directional derivative of the optimal value. And the optimal values tend to be well behaved. If you open up like an LP 101 textbook, they show you this beautiful plot of the optimal value in terms of the right-hand side or in terms of the cost function. And so it's leveraging that that's really allowing us to get the nice performance here. Nice property, I should say. In the interest of time, I'm going to go a little bit faster. So then leveraging these properties, you can perform performance guarantees. I'm not going to talk a ton about this because I don't think this is the audience that necessarily wants to. But like, if you want to prove a performance guarantee for learning with this surrogate loss, it's still hard. And this is the reason that there was a lot of trouble in the literature to establish performance guarantees for many of those existing methods. And the reason is that you want to uniformly bound the difference between your true loss, that piecewise constant discontinuous thing, and your surrogate. But if you want to bound this difference, you still have to deal with the jumps here. Even if your surrogate's well behaved, like this thing is still gross. Okay, so how do you like deal with these jumps? And that requires some analysis for like polytopic fans. It's just a mess. Okay. So what was the insight that allowed us to get this done? Is that if you graph that training loss and think about what happens when as n gets big. So I apologize, this is not the best graph. Just look at the blue line. This is that same example with the blue line where n equals 30. This is the same example, that blue line where n equals 3,000. And what you can see as n grows, the jumps sort of smooth out. They become more frequent and they become smaller, so that if I zoom in, yes, it is still the case that this thing is piecewise constant discontinuous, but if I squint, it now looks very well behaved. And this suggests that you should kind of think about the population loss. What is the infinite limit of the true decision loss? And you recognize it as a convolution, and then all of the kind of basic Fourier theory 101 stuff pops up. You believe that if this density is smooth, then a convolution theory suggests that the overall thing should be smooth. You just have to kind of define what is the right notion of smoothness. And it turns out like the right notion of smoothness is to think about this thing called predictive roughness. Okay, so this is a little subtle. What I'm going to think about for each realization y, I'm going to think about the conditional density of my learner conditioned on y. Okay, so this is a little bit backwards. Traditionally, you think about what is the distribution of y given x, right? Now I'm thinking about what is the distribution of my learner given the outcome. And you can define predictive roughness by this integral, right? Which is basically the integral of the gradient of that distribution. And don't parse the math here. The way that you should think about this object is that it's a way to measure how close this conditional predictive distribution is to being discrete. So here's a conditional distribution with low predictive roughness. Basically, because it changes slowly, the density changes slowly, this gradient is small. So the norm of this gradient is small, the integral is small, the expectation is small. This is one with big predictive roughness. The density changes rapidly, right? It almost looks discrete. Because the density changes rapidly, this norm is big, the integral is big, the expectation is big. Okay, so this R pred is somehow a measure of like how close you are to being discrete. And then given that, you can frame very nice guarantees. There's a lot of guarantees in the paper. I'm just going to give you one for flavor. So suppose you solve the model selection problem that Jay talked about, right? So with a finite amount of data, I go and I minimize over my function class this surrogate. So this is something that's like practically feasible to do. I compare my performance to an oracle that has access to the true decision loss, the one I don't know how to optimize because it looks ugly, and has infinite data. And I think about the regret that would be there. If I choose the step size in that secant method, scaling is 1 over root n, the excess regret looks like this. Okay, so I have two different ones. Let's just look at the polyhedral one for now. It basically looks like 1 over square root n. I have some constants that have to do with the complexity of the optimization problem and the complexity of the regret. So this is nice. This is a true, like a clean bound and a misspecified case for our surrogate losses. All right. Any questions here? And then I'll talk about the more interesting part of this. Okay. So like I said, if that was the whole talk, I'd give myself a B+, right? Like I think that it's just another method. This one's a little nicer in that I have some nice performance guarantees and gives me some insight into the kinds of problems where this is going to work well versus work badly. But I think the thing that really makes this interesting is this unifying perspective. So first, like, what do I mean by unifying perspective? You can always write down a general function class and then be like, oh, all these other functions are special cases of, measurable functions. Like, that's not really a unifying perspective. What I want to point out is that all of these existing things come from these ad hoc arguments, but now I'm going to show you can all see them instead as recast them, I should say, via this PG lens by thinking about them as a specific step size in the finite differencing or a particular choice of convexification of the DC loss. Okay, and then because you can view them that way, it tells you why they don't have good behavior in certain circumstances. And it tells you what you should do in terms of improving the algorithm to improve their practical performance. And there's often small tweaks. Okay, so I'm only going to do a couple of these in the interest of time. Let's start with DBB. So this is differentiating. This is DBB is differentiating black box solvers, I believe is the term. And I won't try to pronounce the author's name. But the authors describe this as a continuous interpolation of the decision loss, trading off informative gradients of faithfulness to loss. But while this was proposed back in 2020, it empirically has very poor performance in benchmarks, right? So people don't really use this. And you can see like it doesn't quite look the way it should over here. Okay, whoops. If you stare at this loss though and squint at it, what you realize is that it's actually equivalent to a PG loss where you're doing the secant differencing in a forward step, and you're taking H to be large, something like 10 or 20. Okay, but we sort of know two things. We know that forward differencing in this setting, while backward differencing is an upper bound, forward differencing tends to be a lower bound. So it's an optimistic bound on the loss. And optimistic learning can be unstable in small samples. And then if you're taking a large H just from like calculus 101, you're not getting a good reference to what the correct derivative is. If you saw in our performance guarantees, we need the H dying like 1 over root n. So you're not going to get the correct asymptotics, right? And so if you just shrink H in this method to be like 1 over root n, you get this green line, which performs much better. Right? So this is what I mean by kind of viewing it through the right lens, suggests why it was working badly before and what you have to do to fix it. Just to do one more in the interest of time, SPO plus is probably like the Thomas Elmerstube and Grigas paper. It's probably the most popular of these surrogate losses. It's a convex loss. It's a very clever duality and scaling argument that gets you there. It has a lot of empirical success. As you can see, like it has the wrong minimum, right? As we talked about under misspecification. So what is SPO plus loss? You don't have to think about it via duality and scaling. Instead, you could just start with the PG backwards loss, right? So this was the loss that I showed you before. It's a directional gradient of this function at the point t in the direction y, and I'm approximating it with a secant size h. Okay. This is this v function, right? I was minimizing an LP. This v function turns out to be concave. This is that DC representation. So minimizing this beast is a little hard because it's DC. If I wanted to construct a convex approximation to this function, what's the standard thing to do? You take the bad concave piece and you linearize it. So let's linearize this thing at its Taylor series at the point y. And if you do that, substitute the linearization back in there, and then move around some terms, you get back the SPO plus loss. So the meaning of the SPO plus loss in this recasting is that it is a PG loss with a linearization, linearizing at y. And that makes sense then, right? So the reason SPO plus has a nice performance guarantee under well specification is that your prediction will be somehow close to y, right? So this is a good idea if you're well specified, but if you're misspecified, your predictions are not going to systematically be close to y, so you're going to have poor performance. Okay. The other insight here, though, is that like SPO plus, if you think about what it's doing then, this is sort of the first iteration of classical DCA algorithm for minimizing a DC loss. Right? Why linearize once? What you should do is linearize, take a bunch of SGD steps, have a new point, relinearize at that point. Now you have a new convex function, take a bunch of SGD steps, relinearize at that point. like a bunch of SGD steps. And that sort of performance modification to the algorithm, right, which is a small modification, I'd argue, but it actually leads to dramatic improvement. So I won't talk about these other ones. This is the Fenchel-Young Loss from Gibbs sampling. This is that CLO loss through the bi-level optimization problem. This is actually a non-surrogate loss relative to combinatorial, relative to Gaussian smoothing. Didn't have a performance guarantee. And then these are some of these extensions. All sort of work together. So I don't want to overwhelm you with benchmarks. Like I said, there's a ton of empirical work in this literature that's all very promising. I just think that that what I wanted to highlight is sort of what does the benefit of this unifying perspective. So we're all at USC. If you want to go from main campus USC to LAX, there's basically only 2 routes to do. So we looked at the standard 5x5 grid benchmark, which is a shortest path problem on this grid. But inspired by this, we sort of embedded 2 nice paths in this thing. So you can either take the red path or the green path, the blue path. The red path is okay most of the time. The blue path is very good, depending on the context, and everything else is trash. So it's just like driving to LAX. You either take the 10, you take the 110, you take anything else, you're just a crazy person. Okay? And then we train these methods. So on this axis, n is the number of data points I'm using. The y-axis is the relative regret to full information optimum. This is a synthetic experiment. I know everything. Okay. The blue line here is if I did that naive decision blind pipeline we started with. Okay. And the purple line is that DBB, differentiating through black box solvers. So already you see a gigantic benefit of just thinking in a decision-focused way. Okay. Now, this is the DBB, this is Fenchel-Young, this is SPO+. There's some differences between them. You can see why SPO+ is sort of popular, right? But you see that if I were to put on the bottom here are these PG methods. And these are all the methods that like the various zeroth order gradients I presented and the tweaks to these existing methods that I was talking about here. So this gap that you're seeing, this is sort of the benefit of this unifying perspective. Right, of understanding why it is that these models work and don't work, and then exploiting that theory to adapt algorithms. Okay, and you see like a 2.5% gap where we're sending the regret basically to zero. Okay, I zoomed in on these methods just so you could see them, though I'd argue that any distinction here is essentially noise, right? But like if you want to see that the differences are quite small. Okay. All right, well, the last thing before I wrap up is that like I've been trying to learn about ISI because I haven't been there. I don't know a lot of folks that are research there. And so I try to think like, given the kind of work that I do, which is very methodological in these data-driven settings and data scarce settings, what are nice places to collaborate? And I think like one nice place to collaborate with researchers that for PhD students at ISI that might be interested in decision-focused learning is developing more of these real-world benchmarks at scale. Right, so a lot of the benchmarks that are used in the decision-focused learning literature are these toy like 5x5 shortest path problems. Right, there are case studies where people do beautiful large-scale things, but they're not really a rich set of benchmarks for those things for different researchers to compare methodology. I think thinking about what is the right set of benchmarks, what would they look like, what would we try to measure on them, how would we support deploying them, that's a great set of questions. The second one I think that's interesting is like, how do you GPUify a solver? So a lot of these methods are solver in the loop. Like I had this method, this Z star, I said it was a solver that I'm going to call. If I'm really running SGD, I have to call that solver over every data point in the batch at every iteration. Okay, so if we could think about calling the solver on a GPU, it dramatically changes the work per batch that has to be done. And there's been some research about this, but I think there's a lot of open questions about what is the right way to like GPUify a solver. And then there's a longer discussion that I didn't talk about today, which is around structured optimization proxies. Like even GPUifying a solver often feels like the wrong answer, right? Just throwing hardware at it. You might say instead, like, I don't really want to call a solver at all, Vishal. I would love to have some sort of proxy problem or proxy function that I can call and evaluate with really low latency, where I give it the inputs that I would normally give a solver, and that will output a nearly optimal solution. That's like a super important problem in a lot of engineering applications. This is a nice, very readable survey about this idea. These are called structured optimization proxies. And how do you learn such proxies for different optimization problems? So I have some work in this area. We have ongoing work on this. That's a lot of fun. But this is another set of questions that functionally come down to like, how do you speed up calling solvers beyond just changing the hardware underneath? Can we think algorithmically or in a more ML way? Okay, so if you remember only one slide, I want you to remember this one. Remember this picture? Okay, so this was like the world's simplest optimization problem, and a lot of these DFL methods fail. So decision-focused learning, though, in practice shows a lot of success, but there's a lot of incomplete theoretical understanding of why this works. And by shoring up that understanding, we better understand, we can get like performance guarantees on some methods, and we can see better algorithms, how to change some of the existing methods to really dramatically improve their behavior. And for linear contextual stochastic optimization specifically, I argue this directional gradient perspective is sort of the right mental model. It allows you to think about all these things under the same lens, and it generalizes naturally to other problems. All right, thank you. I'm happy to take questions. Some notes for people, for PhD students. I'm teaching a decision-focused learning module with Kai Wang from Georgia Tech this summer at the AI Square Summer School in Chicago. PhD students can maybe still apply. You can probably still attend. The person to email is Adam Elmish, one of the organizers. I teach a PhD course here at USC in end-to-end learning and optimization. It's under 3 departments, DSO, ISC, CSCI. It's number 619. It's part of this NSF NRT grant for the OR AI PhD certificate. If you don't know what it is, you should 100% look it up. Most of the PhD students in this audience are going to want to take it. And then if you have some talented undergraduates who want to work in ORAI, let them know. Send them my way. Right? They tend to need joint advisorship between IE and CS. I'm happy to serve as that IE advisor. If you have any questions, you can email me, ask me now. This is the original NeurIPS conference paper. This has a lot of the basic details about the perturbation gradient losses, the unifying perspective, and a lot of the prettier stuff around predictive roughness and benchmarking is coming in the journal version we're writing now. So if you have feedback, today is a great day to tell me so that I can put it in to the journal version. Thank you very much for the time and for the questions. Happy to take them.
Oh, so yeah, we have one question. I'll unmute, allow them to talk if they want to.
Hi, Vishal. Thanks for the wonderful talk.
Hey, Karthik, how are you?
Very good. Thank you. A couple of quick questions. One, in the experiments that you presented, was it a misspecified setting or was it a well-specified setting?
Oh, great question. Yeah, so it is misspecified deliberately. I think that's why you see like MSE has like an 8% relative gap, okay, and it's not getting smaller with more data, right?
And yeah.
Yeah, so the learner, I believe, is, what did we do? I think in this experiment, the learner is linear, but you can see like the blue line actually has like a piecewise linear structure.
Wow. Yeah, and one quick question on the complexity of the perturbed gradient loss, right? Like, so the original problem had 0 regret, but it was kind of like difficult to solve. So you have a difference of convex functions, like which are like, sum of n difference of convex functions.
Mm-hmm.
Does it become solvable with a DC kind of like solver approach, or does it become better with a SGD type of approach, or like do SGDs kind of like have is anything known about the proclivity of SGDs to find the global optima? Like, so any comments that you have on the solvability of the PG loss, that would be amazing.
Yeah. Perfect. Great question and great. I'm going to tell you some things, but I'll be honest and say a lot of things are open. Okay. So first is I didn't prove P equals NP. So minimizing this loss is still NP hard. Okay, because if I could minimize this loss and I'm proving this regret bound to you, then like that weirdly suggests that P equals NP in some way. There's something funny about that. So it is true that it is still NP hard to minimize this loss. Okay. The second thing is you ask, well, can I exploit the DC structure to do something smarter than just running naive SGD? Okay, and that's true, you can. So what you can do is you can run DCA. Okay, so here, I guess the gray line is DCA. And what does that do? That says like linearize the concave piece, run, I think 100 iterations of SGD. Now you have a new learner. relinearize the problem at the new learner, run 100 iterations of SGD, relinearize the problem, run 100 iterations of SGD, etc. And like it does mildly better than the rest of this stuff, but like on this problem benchmark, like this is a small gap, right? So I think it's implementable. It's like SGD with a tweak, but it's not. I don't know. It's not necessarily giving you a ton of improvement. What you do find some improvement is that because this is a non-convex loss landscape, where you start matters, right? So these W's indicate that these were warm started. And I think in this iteration, they were warm started at the solution to SPO plus. So I like ran this, got this guy, and then, or I got the relevant guy at the relevant number of data points, and then did polishing steps using the PG loss.
Wow. Thank you. Thank you. Again, thanks again for the wonderful talk. Thank you.
Yeah, of course.
I don't see anyone else posting questions or raising hands, so I think we can end it there. Thank you, Vishal, for the talk, and yeah, thanks everyone who's still here for attending. And yeah,
Of course. Thank you all very much. Have a good day.
thank you. You too.